Hi everyone, Mrs. Hanson here, welcoming you to our electrochemistry test review session. I've pulled some sample quiz questions to assist you in preparing for your assessments this coming weekend in Electrochemistry Module 6. You may find it helpful to have your formula page as well as your standard reduction table nearby. We may have to look some things up as we solve our problems. Let's begin. In the first category of problems, we began our lessons learning about balancing redox reactions, assigning oxidation numbers, figuring out what is oxidized and reduced, and then applying that into complex redox reactions. Here's a sample question about balancing. It reads, balance the following redox equation in acidic solution. So here I can see an important word clue where balancing in an acid solution. What will be the coefficient in front of water? All right, so we need to balance a complex reaction. We know that the first step is to write out the two half reactions. Let me just write that out. Write out the two half reactions. So I'm going to take the permanganate ion, MnO4 negative, and I'm going to point at the manganese +2 ion, and that's my first half reaction. The second, of course, would take the peroxide, H2O2, and point at the oxygen gas, O2. So I've just decided that the two half reactions must contain the same elements, and I'm just going to separate them as the first step. The next step would have us balance all elements that are not hydrogens and oxygens. Let me write that out in case you're taking notes with me. Balance all elements that are not hydrogen or oxygen. And in this case, there are none. Manganese on the left side is balanced on the right side, with both of them having a coefficient of 1. The next step, and as a third step in our acidic solution, is to balance the oxygens by adding waters. So let's test this out in the first reaction. Notice on the left side there are 4 oxygens, and on the right side of this half reaction there are none. I need to add 4 waters to the right side so that the oxygens match. Let's do the second half reaction. On the left, there are 2 oxygens. On the right, there are 2 oxygens, so we're done. The fourth step is to balance the hydrogens. Let me write that out. Balance the hydrogens by adding protons, which are hydrogen ions. And I'm emphasizing hydrogen ions because I have to make sure that I remember to put H plus and not just H. So let's do that, step 4. In this reaction, the first half reaction, I can see there's a total of 8 hydrogens. To balance those on the left side, I have to add 8 positive protons. How about in the second reaction? Well, here on the left side, I can see 2 hydrogens. So I'm going to need to balance that on the right side by adding 2 protons. The hydrogens are now balanced. In your next step, we balance the charge. And we do that by adding electrons to the more positive side. There, got that written out. Let's check where we're at right now. In the first half reaction, on the left side, I have 8 positives and 1 negative for a total of +7 overall. And on the right side of this half reaction, I have a manganese +2, so the net charge is +2 overall. Which side is more positive? Well, it's the left side. So here I can see I need to add 5 electrons to the left side so that both are now +2 overall. Let's do the same strategy for the second half reaction. The second half reaction has a +2 on the right side overall and a 0 charge on the left side overall. To the more positive charge, to the more positive side, we'll add 2 electrons so that both sides are now at a net 0. Step 6. In step 6, what we'll want to do is make sure that the electrons lost equal the electrons gained. Leo must equal Ger. So in our first half reaction, we can see that there were 5 electrons gained, and in the second half reaction, there were 2 electrons lost. They must be the same number. Lowest common denominator for a 5 and a 2 is a 10. So in the first half reaction, we'll need to double all of the coefficients we figured out so far. And in the second half reaction, we'll need to distribute a 5 to make sure that the 10 electrons gained in the first half match the 10 electrons lost in the next. Let's distribute those coefficients and add the reactions back together. Here's everything on the left side. 2 times 8 is 16 positive protons. Let me change color so we can see that up here better. I'll make that green. We have a total of 8 times 2 is 16 positive protons. 2 times 1 is 2 permanganate ions. 2 times 5 is 10 electrons. There's everything we have in the first half reaction. How about the second? 5 times 1 would be 5 units of the peroxide. So there's our distribution of the coefficients while adding the 2 equations back together. Let's do the product side next. In the first half reaction, 2 times 1, we have 2 units of the manganese +2 ion, plus 2 times 4 is 8 waters, plus, now down to the second half, 5 times 1 is 5 oxygens, plus 5 times 2 is 10 hydrogens, plus 5 times 2 is 10 electrons. So with our step 6, we distribute and add back together, making sure oxidation equals reduction. And finally, step 7 is to simplify everything you can. Let me use a red pen and simplify out what we can. Here I notice on the left side we have 16 positive protons, and on the right side there are 10. I'm going to cancel the 10 and leave a remainder of 6 positive protons on the left. Of course, we know the electrons will cancel. That was the purpose of all of this, so let's get rid of them. How about the waters? Nope, there's only water on the right side. It looks like we have simplified everything for this final answer. We have 6 positive protons plus 2 permanganate ions plus 5 peroxides. H2O2 is hydrogen peroxide. Pointing at 2 manganese plus 2 ions, 8 waters, and 5 oxygens. We are balanced now by mass and charge. And ultimately, your quiz question will ask you about a coefficient related to just one ingredient. And in this question, it was about the water. And so I can see that 8 is the coefficient in front of the water. How'd you do? Well, let's try a second balancing question. This time we'll do it in a basic solution, and I will not write out all the steps. So take a minute, pause the video if you need to, and just kind of read through and decide what we're doing. We're asked to balance the following redox in a basic solution. What's the coefficient of hydroxide when we're done balancing? So here's our equation. MnO4 which is a -1 charge, is changing into Mn plus 2, very similar to the last slide we looked at. The next one I have is HCOOH. And you know, friends, I think it often much easier to just combine like elements to make counting easier. So instead of me writing out HCOOH in the half reaction, I'm going to write out H2CO2, combining like elements using subscripts to help me tally. I'm less likely to make a counting mistake when I do that. So the second half reaction will be H2CO2 pointing at the carbon dioxide. So there's our two half reactions. Let's go to work. We're going to balance all elements that are not hydrogen or oxygen, and that is accomplished already. We then move to balancing the oxygens by adding water. In the first half reaction, I need to add 4 waters to make sure I have 4 oxygens on both sides. In the second half reaction, notice that we have the oxygens balanced already, so no need to do anything about oxygen. The next step, let's tackle the hydrogens by adding protons. In the first half reaction, I can see 4 times 2 is a total of 8 hydrogens. So I'm going to add 8 protons, 8 hydrogen ions to the left. And in the second half reaction, I need to add 2 hydrogen ions to the right. Now let's balance charge by adding electrons to the more positive side. On the left side of the first half reaction, we see a total of +7 as the net charge overall. And on the right side, we're at a +2 as the net charge overall. So to the more positive side, I will add 5 electrons to now make both sides +2s overall. In the second half reaction, the first side is a 0 and the next side is a +2. To the more positive side, I add 2 electrons. So now that both sides are 0. Lowest common denominator for a 5 and a 2 is 10. So once again, we're going to distribute through and make 10 electrons lost and 10 electrons gained. I'm going to add together the two half reactions and distribute the coefficients at the same time. 2 times 5 is 10 electrons plus 2 times 8 is 16 hydrogen ions plus 2 times 1 is 1 permanganate, MnO4 negative. The second half reaction, 5 times 1, gives me 5 H2CO2. There's both sides added together and distributing the coefficients. Let's do the right side next. 2 times 1 is 1. 2 times 2, Linda. 2 times 1 is 2 Mn plus 2s. That tongue-tied there. 2 times 4 is 8 waters. We'll go down to the second half. 5 times 1 is 5 carbon dioxides, giving us 10 hydrogen ions and 10 electrons. What can we simplify? Let me take my green pen and simplify what we can. First of all, electrons should always cancel out, so I'll get rid of them. I'm noticing that I have 16 hydrogens on the left and I have 10 hydrogens on the right. I'll simplify by eliminating the 10 protons from the right and leaving a remainder of 6 on the left. Do you see anything else? It looks like we have simplified all we can. And friends, if this were an acid solution, we'd be done. But it's not. It says we're in a basic solution. So we know there are additional steps to neutralize the protons. On the left side, we have 6 positive protons. We need to neutralize those by adding 6 hydroxides to both sides. So I'm going to add 6 hydroxide ions to both sides. And remember, when we do so, 6 positive protons and 6 hydroxides is equating to 6 waters. So the 6H plus and the 6OH negative combine to make 6 waters and are not separated any longer. Notice that the 6 waters here and the 8 waters here on the right side can simplify. I can eliminate the 6 waters from the left and simplify the waters on the right for a remainder of 2. The final answer, and again, remember that the quiz can ask you for any coefficient. This one is asking for hydroxides, but it could be for any of them. So I'm going to write out the final answer. I got to go back and put those 2's there. 2 times 1 is 2 MnO4 negatives. Right there, 2. So I have 2 MnO4 negatives plus 5 H2CO2s. And that's it for the left side, isn't it? Pointing at 2 Mn plus 2s, 2 waters, 5 carbon dioxides, and 6 hydroxide ions. And since that's the coefficient we were asked for from your multiple choice selection, you would pick the coefficient of 6. So I've done one review question for acid solution and one review question for a base solution. I have one more example problem from this section, and that's a question that asks us to count how many electrons are being transferred in the equation 2 ClO3 negatives plus 12 positive hydrogens plus 10 iodides, that's I negative, iodide, forming molecular iodine, molecular chlorine, and 6 waters. How many electrons are being transferred? To answer this, we need to separate out the 2 half reactions and balance them by charge. So here we have 2 ClO3 negative. That's called the chlorate polyatomic ion. And I'm going to point at the chlorine molecule. There's the first half reaction. The 10 iodide ions will point at the 5 molecular iodines, I2. And you know that we'll end up with hydrogens and waters through the process of balancing. You can see why we add 6 H2Os to the right side to balance the oxygens, and onto this side we would need 6 times 2 is 12 hydrogens. So this is the first balanced equation. And then down below we have 10 I negatives forming 5 I2s. What we need to do to answer this question is figure out how many electrons do we add to the more positive side. So here we have 12 hydrogen ions, so that's 12 positives, and 2 chlorates. So the net charge is 10, and it would be 10 electrons is what I'm trying to write there, 10 positive. There we go. It's at a plus 10 overall. And on this side, it's at a 0 overall. 12 protons and 2 negative ions gives me a plus 10. So to the more positive side, I know that I would need to add 10 electrons. Now both sides are at 0. Down here, 10 units of a -1, and this side is neutral. To the more positive side, we would add 10 electrons. How many electrons are being transferred? Well, there's 10. And the way that I needed to solve for that problem was separating out the 2 half reactions and then balancing the charge by adding electrons to the more positive side. The next set of problems will focus on galvanic cells or voltaic cells. We know that those 2 words mean the same thing. And I just grabbed some examples from our quizzes related to calculating voltage, deciding what's oxidized, what's reduced, and looking at standard cell notation. Let's take a peek at our first example problem written here. It says consider a galvanic cell based on the following reaction. We have iron as a +2, reacting with the dichromate ion, Cr2O7 -2, going to the iron +3 ion, and the chromium +3 ion, and it happens to be in an acidic solution. Calculate the voltage of a standard cell carrying out this reaction. From our balanced equation, I can see iron going from a +2 to a +3. Iron is becoming more positive. I know that means that it's being oxidized. It's the process of oxidation, and we learned that oxidation always occurs at the anode. Dichromate going to chromium +3 is being reduced. Reduction always occurs at the cathode. Now, from a screenshot on your standard cell reduction table, I just grabbed the iron +3 going to iron +2, and notice that its voltage here is 0.77. So this is 0.77 volts. And in the second screenshot down here, I grabbed the dichromate forming chromium +3. Do you see that? I just want you to really take your time and become familiar with your standard reduction table. That value given to us in a table, we had to look it up, is 1.33. We know that to calculate standard E cell, it's the voltage from the cathode minus the anode. The little trick I shared with you in our notes was lining up the two C's next together. The E cell is the cathode minus anode. In this particular problem, the cathode value was 1.33 volts minus the anode value of 0.77 volts. When I subtract, let me grab my calculator, 1.33 minus 0.77, my screen reads 0.56 volts, and that's the standard E cell. Not that this is a challenging problem, but if I make a mistake, I'm most likely to make a mistake by not finding the proper half reaction voltage from the standard reduction table. So that was the purpose of picking this problem, was to make sure that you want to find the dichromate Cr2O7 negative forming the chromium +3. Find the proper voltage by matching those two half reactions. Perfect. Good work. All right, what's next? Here we have an electrochemical cell with a zinc electrode immersed in a 1.0 molar zinc ion solution and a silver electrode immersed in a 1.0 molar silver ion solution. These are standard conditions. Calculate the standard cell potential for this cell. Well, remember that the voltage is always given to me as a reduction in the standard reduction table. So notice that the zinc and the silver are both written as reduction half reactions, although we realize that one will have to be oxidized and the other will have to be reduced. How do we know by looking at these two voltages which would be the reduction half reaction and which is the oxidation half reaction? And just remind yourself of the note we made during our lessons that the more positive voltage value is higher up on the standard reduction table, the more positive values are up high, is always going to be reduced. So between negative 0.756 and positive 0.800, you can see the silver value is more positive, and therefore it's going to be reduced at the cathode. the more, or I should say the less positive number is going to be oxidized at the anode. And now once I made that decision, E cell is very simple. The more positive number, 0.800 volts, which is occurring at the cathode, minus negative 0.756 volts, which is the value at the anode. You're subtracting a negative number, so you end up adding the two. 0.8 plus 0.756 is 1.556 volts. Now remember, that number makes sense because it's positive. That means that it's a spontaneous reaction, that this voltage is actually producing work, something you could capture to do work with. If I had accidentally subtracted in the wrong way, if I had accidentally made negative 0.756 minus 0.800, I would get a number that was negative 1.556. The negative voltage would tell you that that's a non-spontaneous reaction. And this is clearly saying you have to decide which one is being oxidized and reduced to make voltage. So it must be positive when you're finished. Good. Okay, these are simple if we just understand how do I know which one to put first and second, cathode minus anode. Let's take a peek at a next example on the same topic. Which of the following statements is true concerning electrochemical cell depicted below? Well, in the first half of our standard cell notation, I see barium as an element, and I'm going to point as barium as an ion. Ba starts as a neutral atom. The line separated into barium plus 2. So I would know that this would be solid and aqueous, just kind of putting those standard states in there. And in the second half, the second cell, you can see the sodium ion is written first. So you would have Na plus aqueous. And on the product side, you can see that that would be Na as a solid. Now, when we want to look at the conditions here, sodium going from +1 to 0 is being reduced. It's getting more negative on the number line, and we know that that occurs at the cathode. Barium is going from 0 to a +2, which we know is being oxidized, which occurs at the anode. To calculate E cell, we take the cathode, which we said was sodium, negative 2.71, minus the anode, which was the barium, negative 2.91. Hit that with me on the calculator and see what we find. The value of negative 2.71 minus a negative value of 2.91. And my screen says positive 0.2. Just put that as a positive sign to see. So which choice? Read through them and see what you can find. Letter A, the cell reaction is spontaneous with the cell potential value of 0.2 volts. Choice B gives me the same, saying it's non-spontaneous with negative 0.2 volts. The cell reaction is 5.62 or negative 5.62, or the cell is at equilibrium. And if that were true, the E cell value would have come out to 0. Well, when solved properly, we can see that letter A gave us the positive 0.2 volts. The standard cell notation, barium went from 0 to +2. That's oxidation. Sodium went from +1 to 0. That's reduction. That's how we knew to take reduction minus oxidation, cathode minus anode. Cool. I'd like to do one more on this topic. Looking at a galvanic cell as drawn below, the contents of each half cell are written beneath each compartment. So here I can see in this first compartment where I have the platinum as the electrode, I can see that I have MnO4 negative, Mn plus 2, and hydrogen ions. So notice that I'm kind of separating out the two half cells. So I'm going to just make a note. MnO4 negative is pointing at Mn2 positive. That's how I'm reading that in solution. That's the first half cell. And notice that these are both aqueous ions, and that's the reason we have the platinum electrode. That's an inert electrode, because as we discussed in our lessons, there's no way to hook an alligator clip to an aqueous ion. So we hook the clip to the platinum, which then serves as a surface electrode for the reduction occurring here. What's in the next half cell? Notice that chromium ion is written first, Cr plus 3, and written next is Cr2O7, 2 negative. And these two values here, they're just telling us that it's an occurring in hydrogen ions. So it's an acid solution for this complex, an acid solution for the complex redox reaction. So what's being oxidized? What's being reduced? First off, I can toss out the hydrogen ions as a choice because it's there to serve as the acidic solution when I'm balancing an equation. Just like if this had hydroxide ions, I would know it's being used to balance a basic solution. They will not be your choice. The other really important clue is notice that the oxidation and reduction are always reactants. So I can toss out Mn plus 2 as a choice because it's a product, and I can toss out dichromate ion because it's a product. The agents are always reactants. So now I've got it down to two choices. Which one is being oxidized? Well, if manganese in this first reaction, I'm going to assign an oxidation number to it. We know oxygen is always a -2, making manganese a +7. +7 going to +2 is getting more negative on the number line, so that is reduction. Chromium going from a +3 to a +6. Now remember how I did that? Oxygen always a -2. Making the two chromiums have to give me a net of +12. So each chromium must be +6. When chromium goes from +3 to +6, that is oxidation. The chromium +3 ion is being oxidized. Now I picked this for several reasons because I wanted to remind myself how to read these half cell standard notations. Remember that what's written first is a reactant, what's written next is the product. We can toss out the products as choices of what's being oxidized and reduced. They must come from the reactant side. Now this was, an interesting problem. It just simply asked which species is being oxidized. It was not a quantitative question, but we could easily calculate E cell because we've determined what's being oxidized and what's being reduced. The manganese was being reduced as 1.51 volts, and we said the chromium was being oxidized at 1.33 volts. And I would simply subtract those two voltages to find the standard potential of this galvanic cell. Let's move to a third topic, cell potential and free energy. Gibbs free energy, delta G. We know that delta G, Gibbs free energy, is spontaneous when it is negative, right? And that an E cell is spontaneous when it's positive. And that an equilibrium constant favors the forward direction with a larger number. And those are equations given to you on your formula page that we developed in our lessons. Delta G is equal to negative NF times the standard E cell, where we know N stands for the number of moles of electrons transferred during our redox reaction, and F is Faraday's constant. F you don't have to memorize, but I know you end up doing anyway because you write it so often. 96,485 coulombs per mole of electron. The reduction potentials for gold 3+ and nickel 2+ are as follows. Gold plus 3 electrons is given to us as a standard cell potential at 1.5 volts, and nickel is given to us from the standard reduction table as negative 0.232 volts. Calculate the delta G standard conditions for the following reaction. Let me rewrite this with you. 2 Au plus 3s plus 3 NIs will point to 3 Ni2 plus and 2 Au. Au starts as a +3, that's gold, and goes to a 0. It is being reduced. Reduction we know occurs at the cathode, and it has a value of positive 1.50 volts. Nickel is going from 0 to a +2. That is being oxidized, which occurs at the anode, which had a value of negative 0.232 volts. Calculate delta G. One of the first things we need to do is calculate E cell. Now E cell is found by taking the cathode minus the anode, which we said the cathode had a value of 1.50 volts, and the anode had a value of negative 0.232 volts. Subtracting a negative number means we'll add them together. When we add that together, hit it with me, 1.5 plus 0.232, do you get a value of 1.732 volts? That's the E cell part of our equation. Next thing we want to do is to make sure we figure out how many electrons are being transferred in this equation. And just use the clues up here in the half reactions. Notice that in the first half reaction, 3 electrons are being used to balance charge. And here in the second half reaction, 2 electrons are being used to balance charge. What's the lowest common denominator for a 3 and a 2? Well, it's a 6. You know that when you distribute to balance the electrons lost and gained, it'll end up being 6 overall. You kind of see that here anyway when you separate the 2 half reactions. 2 units of a +3 is a +6 overall. 2 Au +3s will require 6 electrons to balance the charge. Look at your second half reaction. You had 3 nickels pointing to 3 nickel ions. It would require 6 electrons to balance the charge to make Leo equal Ger. So N is 6 moles of electrons. Now we have what we need to solve for delta G. Negative 6 moles of electron times Faraday's constant, which we said was 96,485 coulombs per mole, times the E cell, which was 1.732 volts. And this is going to come out negative, as we predicted. A positive voltage represents a spontaneous reaction. Delta G better be negative because negative delta G represents a spontaneous reaction. When you hit these three numbers out on your calculator, 6 times Faraday's constant times 1.732, it's a very large number. Negative 100.2672.12, but keep in mind that that comes out in joules. So divide by 1,000, just move the decimal 3 spots over, and you'll find 1002.7 kilojoules. You probably want to do 3 sig figs, so you'd probably see 1.00 times 10 to the 4th kilojoules overall. One, two, three, not the 4th. That's 3 decimals. Let me repair that. That's the correct magnitude for 1002.7 with 3 sig figs is 1.00 times 10 to the 3rd kJs. There. That's not so bad, right? We're doing good. All right, here's the next example. We're asked to determine the standard cell potential and the cell potential under the stated conditions for the electrochemical reaction described here. Tell me if it's spontaneous or non-spontaneous at the set of conditions of standard temperature. So I know that this is called the Nernst Equation. And the Nernst Equation lets me calculate the E cell for non-standard conditions by using the equation as follows. The standard E cell minus 0.0592 volts over N log Q, where Q represents the reactant quotient, products over reactants. Q would be products over reactants using the concentrations provided within the standard cell notation. So let's examine the products first. The product gives me a solid silver and solid mercury sulfide. Pure solids and pure liquids are not used in an equilibrium expression, so there are no values for the products. I'll just represent that as 1. Let's look at the reactants. Here's mercury in its pure form as a liquid. Pure liquids are not represented in an equilibrium expression. Here we have an aqueous ion of sulfide. So it would be used. We need the concentration of sulfide raised to the 1st power because its coefficient is a 1. And we'll also include the silver ion because it's an aqueous ion and its concentration would need to be squared due to the coefficient of 2. So let's plug that in. Sulfide was given as 0.1 and silver ion was given as 0.25, and that would need to be squared. 1 divided by 0.1 and 0.25 squared. When I hit that on my calculator, hit it with me, my screen reads 160 as the value of the quotient. What about N, the number of moles, and E cell? We've got some work to do here now to figure the other 2 components out. These 2 values, these half reactions, are provided here to help us figure out the overall equation. Notice that on the left, I have silver ion, and on the right, we have silver solid, and that is positive 0.7796. Now on the product side, let's see, we have solid HGS and Hg going into the molecular form of mercury and sulfide. And so the next half reaction would look like Hg plus 2 electrons, giving Hg and sulfide. And that, of course, was given to us as 0.7 negative value. I know that silver in this equation is being reduced. Silver starts as a +1 and goes to a 0. Since silver is the more positive number, we know that this is going to be the reduction half reaction. And the less positive number is always going to be the oxidation when the reaction is spontaneous. So to calculate E cell, reduction value 0.7796 volts minus the oxidation value of -0.70 volts gives us a standard value of, let's hit that out. My screen reads 1.4996. Can we just round that and make that 1.50 volts? All right, we have Q, the reaction quotient. We have E cell standard is 1.5 volts. And what about N, the number of electrons? Well, just look at these two half reactions that are given. 2 electrons are being gained and 1 electron is being gained. I know that I would flip the second half reaction when balancing the equation, but I can tell that when I balance that, I know that there's 2 electrons involved, that I would distribute a 2 through the first half reaction, meaning that the equation is balanced when the number of moles of electrons is 2. And we have what we need now to just solve. E cell is 1.5 volts minus 0.0592 over 2 log of 160. That's the Nernst equation. We know that this is going to be a spontaneous reaction, both in standard and in non-standard condition, because the voltage came out positive. Well, let's hit this just so we have a final answer. 1.50 minus 0.0592 over 2 times the log of 160. My screen is reading 1.43 volts. So this is at standard conditions, and this is the non-standard conditions, which is what both were asked for. Good, we get to practice the Nernst equation with that example. Excellent. What's next? Calculate the equilibrium constant for the following reaction. The equilibrium constant for the following reaction. AgCl as a solid, forming Ag plus and Cl negative. Well, I know the relationship between E cell and the equilibrium constant is given as 0.0592 over N, the number of moles of electrons, times log of the equilibrium constant. We're given these two half reactions below to work through and find standard E cell. So I used my standard reduction table, and I found these two half reactions, and we need to use these two half reactions to create the target equation. So I noticed the first thing written in this target equation is AgCl as a solid. AgCl is written in the first half reaction. So let me just write that. AgCl plus 1 electron is giving me elemental silver and a chloride ion with a voltage of 0.22233. The first product is given to me as Ag plus. And Ag plus is written over here in this side of the equation. Now remember, we're going to need Ag plus on the product side, so I'm going to need to reverse this equation. It's written with it on the left side, but the target equation has it written on the right side. So let's reverse the equation as it's written, writing Ag plus with an electron on the right, and elemental Ag on the right. And when you reverse the equation, you know that the voltage would become negative. Now I'm not going to do that because that will be taken care of when we say cathode minus anode, that minus side automatically will reverse the sign. So don't switch the sign. We'll automatically take care of that when we calculate E cell by going cathode minus anode. That's what this minus sign is doing for us. It is switching the sign automatically in that equation. So don't do it twice, so you'll get an error. Now see what we've done? Let's just kind of prove to ourselves. Elemental silver canceled in that equation, as did the electron. And what we did was to build our target equation. We can see that the first half reaction was reduction. It was gaining electrons. And in the second half reaction, this was oxidation because it was losing electrons. So E cell in this equation, with reduction being 0.22233 volts, and the anode for oxidation was 0.7996 volts. When I subtract those two, I actually get a negative voltage, don't we? So the E cell coming out here shows a non-spontaneous reaction with a voltage of negative 0.57727 volts. I know it's non-spontaneous with that negative voltage, and just based on my two half reactions, I'm able to tell that the electrons lost in this reaction mean oxidation. So that larger number was actually oxidation this time. What else do we need to know? Well, we need to know N, the number of electrons, which we can see from our two half reactions, is 1. 1 electron lost, 1 electron gained. So we have what we need to just plug in and solve for K. The value of E cell as a negative 0.57727 volts is 0.0592 over 1 times the log of the equilibrium constant. Solve for K. I'm going to just simplify, doing a little algebra. You can see negative 9.75 giving me the log of K. So 10 raised to the negative 9.75 is K. K should be a very, very small number to indicate that the reaction is not favoring the forward direction. And my calculator reads 1.77 times 10 to the negative 10 for the value of K. And that's me just solving this algebra one step at a time. That was great work. All kinds of incorporated equations. Here are some questions from quizzes that students have emailed me, and I wanted to put those into this review session as well. So the first of emailed quiz questions reads as follows. What is the correct cell notation for a voltaic cell based on the reaction below? All right, so I can see copper plus 2, and it's pointing to copper as a solid. And I can just clearly see that that would require 2 electrons, and that half reaction is balanced. I can see on the left side lead as a solid, and it's pointing at PbSO4 as a solid. Now, to keep it balanced, I also need to include the sulfate aqueous ion in that half reaction. And you can see that this would be 2 electrons lost to balance charge. So what is the cell notation? Remember that by standard, we always write the anode oxidation to the left in standard cell notation. And the oxidation is occurring with the lead. So this is the oxidation, oh dear, OX, oxidation. Let me write that more neatly. So the first species would be the solid lead, and then a line separating that it formed PbSO4 solid, so that's the reactant going to the product. That's a solid. And I also need to include the sulfate aqueous ion in this half cell to keep the equation balanced by both mass and charge. I will draw 2 lines to represent the salt bridge separating the anode from the cathode. The cathode is the site of reduction. The first species was written as Cu+2 is an aqueous ion. And I'll separate that with 1 line to the copper solid. And that's all I see in that second part of that standard cell notation. So this is your answer. If I made a mistake, it was just being a little unsure what to do with the sulfate, but it does need to be included because the reactions, even though we're separating them into anode and cathode, they must be balanced. Good work. Okay, home stretch, my friends. Hang in there with me. Here's one that was missed and emailed for help. It reads, the balanced half reaction in which dichromate is reduced to chromium-3 is a blank process. And it says 3 electron, 4 electron, 12 electron, 2 or 6. So how many electrons? Well, if I struggle with this, it might be in remembering what dichromate is because it's not given in this problem. And we must know the polyatomic ion. We've written it several times. Dichromate, Cr2O7, carrying a -2 charge. And we're going to point at the chromium +3 ion. Notice that the Roman numeral tells me the charge. Now just balance this just as we did at the start of our exam review. We're going to balance all of the elements that are not oxygen and hydrogen first. And we do that by placing a 2 in front of the chromium to balance the 2 in dichromate. We'll add 7 waters to balance the oxygens to the right. We'll add 14 protons to balance the hydrogens to the left. Now let's balance charge. The net charge on the left side is +12. The net charge on the right side, 2 groups of +3, is +6. To the more positive side, we'll add 6 electrons so that both sides now equal +6. This is a 6 electron process. So this was a little weird only because it's asking you to balance a half reaction, but kind of didn't say that right off the bat. And if I couldn't write dichromate, I would really be stuck. And my last equation, my last question for our review, kind of looking at the very last topics on electrolysis and plating of metals. What charge in the unit coulombs would be required to deposit 1.5 grams of magnesium from a solution of magnesium ion? I want you to just think of these as nothing more than stoichiometry problems or unit cancellation problems, right? Just cancel units. Here's what we're given. We're given 1.5 grams of the element manganese. And what do we want? We want to know the charge in coulombs. So given to want. Start by writing out what we're given, 1.5 grams of Mg. I'll convert that into a mole by using the molar mass of magnesium. Look on your periodic table. You'll see it written as 24.3 grams. Now we want mole of magnesium to cancel, so I need to place that. And how many electrons are being exchanged when magnesium turns into magnesium ion? Well, that's 2, isn't it? So there are 2 moles of electrons in every 1 mole of magnesium. And now we can cancel moles of electrons out by using Faraday's constant. We know that there are 96,485 coulombs of charge in every 1 mole of electrons. We're there. Step 1, the grams canceled. Step 2, moles of magnesium canceled. Step 3, moles of electrons canceled. And we've arrived at the unit we wanted, coulomb. So let's hit it out. 1.5 divided by 24.3 times 2 times Faraday's constant. I have a big number, 11911.7. We're allowed 2 sig figs, so let's say that's 1.2 times 10 to the 1, 2, 3 to the 4th power. And that would be my answer. And that's the last problem that's been emailed to me so far. I'll encourage you to keep the good questions coming, and I'll stop my review session at this point. Email me with any questions as always. Have a good day, everyone.